You're storing it up in the daytime when you don't need it, and in the evening when you do need it, it's automatically being let out again. There's no wires involved, no controllers or anything like that. It's just, that's why they call it smartboard. It's intelligent within itself. Now, last time I was here, this underfloor heating manifold was mounted on a piece of plywood because they hadn't actually built this wall then, but now it's been put in its final position, and what it's lacking now is a heat source. It can either be hooked up to a boiler, or in this case the ground source heat pump. And these bits of sleeving here are just where it goes into the screed. Once it's actually buried in the screed, it's just the pipe so that it can dissipate the heat evenly throughout the building. So the old windows, although double glazed PVC-U, have been replaced with triple glazed wooden frame windows. These will give an even greater level of insulation, especially with the argon gas, which is between the 3 glazing units. Don't forget, these windows use low E glass, which has a special coating on the inside to trap the heat. In this garden with a limited area, instead of using the pipe in the trench method, we've used a borehole for the ground source heat pump. This has involved getting a drilling rig in to drill 80 metres down into the earth below. We've had the geological survey done on the ground, so it's not a hit and miss operation. We actually know what's under the ground metre by metre. We know at what depth we're going to reach the water table, and then we go down through there. We know what's below there, and we're aiming for about 80 metres deep. And that will take the ground source heat collector pipe down into the ground, deep down into the ground, so that it can extract that heat year in, year out, all through the seasons, at a fairly regular, somewhere between 3 and 5 degrees centigrade, they tell us. Now I'm just going to explain this, because once they start drilling, they're going to chuck us off the site. They only want the skilled guys on who know what they're doing. All the spectators have got to go outside. So I'll just show you very briefly what's going to happen. Once that hole is drilled, they drop this pipe down here. Now this pipe is a very strong pipe, polyethylene pipe. It's made to withstand that extra pressure. Because it goes so deep, it's going to have a massive static head on it. So it's made to withstand that. Onto the end of that pipe, to make sure that it doesn't float back up and that it goes right to the bottom of the hole, they put this massive weight. This is bolted onto the end of that pipe. That's twin-walled pipe, so the water and glycol mix, which is over here, is going to be put into the pipe, and the pipe's going to be lowered down into the hole as it goes, filled up, weighted, and that will sit in there. The water will then be pumped down, the water and glycol pumped down into the heat, grab the heat, and then away. So, a metre below the ground, they terminate the pipe, cut it off there, and then change it to a couple of elbows. That pipe can then go in. It's a thinner walled pipe because it hasn't got so much pressure, and that will then go directly into the heat pump. But there's one very important thing, because at that point, it can actually freeze in the ground. And if it freezes in the ground, of course, the whole thing just locks up solid. So what we have is insulation here, which stops the transfer from the cold to the hot, so that those remain independent. There's one other thing that's happening here. Because we've got a rainwater harvester, which is basically a big tank that sits under the ground to collect the rainwater for use, there is a possibility that if that cold pipe goes past the rainwater harvester and just takes heat out of the rainwater harvester all the time, you could actually freeze the rainwater harvester. So this insulation is very thick, Class O insulation, very high grade, to make sure that that doesn't happen. Well, the drilling's finally underway, and as I say, they're going down 80 metres. Now, you might wonder how they arrive at that magical figure of 80 metres. They're not drilling for oil or water, so in a way, they can go as deep or as shallow as they like from that point of view. But the 80 metres gives them the required length to match the heat requirement of the house. In other words, they've done an assessment on the house, found out how much heat the house will need, and then they've measured that distance per metre of ground source heat collected, if you like, and that gives them the 80 metres down into the ground. Of course, if it was a bigger house, they could go deeper. And these guys are telling me that they can go down 800 metres.
So with the borehole complete and the pipework lowered and grouted in, the pipe is now in the trench and it's ready to be connected up to the heat pump. The glycol is added through the pump unit, which mixes the solution and works the free air out of the water. The glycol concentration is carefully checked, and the solution is then fed into the heat pump to complete the circuit. In order to put in the rainwater harvester, we need to dig a large hole. Pipes from the roof guttering are buried under the patio to drain into the storage tank. The water is pumped on demand back into the house via a filter which keeps it clean. This system can store around 1,000 litres of water, which is used in the house to flush the toilets and to run the washing machine. It can also be used to water the garden. Well, there's definitely a cold wind blowing today and winter is nearly here, and the Worcester Eco house is just about in its finishing stages now. What we can see behind us is really the cosmetic work. All that technology is now hidden away. To the casual bystander, they wouldn't know that it was any different to any other house, and I think that's the key. The garage is gone, there's going to be a little bit of car parking space there, and then the occupiers can use that garden as if it was just an ordinary garden. Well, here we are back at the house. It's all finished and winter has well and truly set in. By British standards, it's a very cold morning indeed. In fact, if I measure the ground temperature here, see what we've got. We've got actually -9 on this device here, which is very cold. That's not the air temperature, that's the ground temperature, but you would think that ground source heat wouldn't be doing very much on a day like today. And also the solar panel on the roof is frosted over. And again, you'd think, well, there's not much going on, but the sun is shining, the sun's bright. So let's go inside and see exactly what kind of heat we're getting out of these technologies. Now I've come inside the house, I'm immediately struck by how much warmer it is in here. It really is very comfortable indeed. But the amazing thing is, like I say, that the heat is actually coming from outside. It's coming from below that very cold ground. It doesn't matter whether you've got the pipe in the trench system or in this case the borehole. The idea is that it's taking the heat out of the ground and it's bringing it in through these pipes here, which are heavily insulated because they're actually very cold. Even though I say it's taking the heat from the ground, you wouldn't actually know that there was any heat there at all. It's coming in at about -1 degree centigrade, which is pretty cold. But it goes through the heat pump, and that heat is extracted through the heat pump so that when it comes out of this pipe here, it's really quite hot. And that is useful heat which is being fed into the accumulator or buffer tank, which is tucked away around the back here. I'll show you that in a bit more detail in a minute. But you can see an awful lot of equipment here. There's a lot of technology. It's all on display. Normally you wouldn't have to fill your conservatory full of all this sort of thing. It would be tucked away inside cupboards or in the cellar or in the loft or anywhere else. So don't be alarmed by the fact that this looks like the boiler room for the Queen Mary, because you won't need to have it all on display. You probably wouldn't have all this equipment. So let me just have a look at what's going on with the solar panel, because that's also working. So up here we've got the unit that controls the solar panels up on the roof, and the flow and return here. This is the heat actually coming out of a solar panel now down through this pipe here, and we can actually find out what temperature that's at from this control panel here. If I just press that button, it will tell us what the sensor on the roof is telling us, and we're just about getting 40 degrees centigrade from that solar panel on the roof. So even on a very cold day, when you want your overcoat on, that's producing really useful heat, and that's pumping down into the cylinder. And if I press that button now, we can see that the cylinder currently is at 35 degrees centigrade. So what it means is that even on a very cold day like today, that solar panel on the roof is contributing half the hot water output for the whole house, just heated on the sun alone. Now, there's an awful lot of pipe work here, there's an awful lot of electronic controls, and it all looks very complicated. And I'd just like to give you a quick overview of the system without getting into too much technical detail, show you that it's not actually half as complicated as it looks. If I just move out the way, you can see in the corner here is the buffer tank or accumulator. Now that basically is your heat bank. It stores the heat from wherever it comes from. In this case, the ground source heat pump is being fed into it. Now that will sit there building up heat, and when the underfloor heating or the cylinder requires it, it will be pumped out of there into the cylinder or into the underfloor heating. And it'll do it based on automatic controls, so it'll take whatever's available. If, for example, as is happening now, the solar panels on the roof are providing water for the cylinder, then this buffer tank won't be required at all. And then of course it's fed through into the heating system, which is down here. It's all individually controlled to each room, each zone. Upstairs we've got the radiators. All that is fully automatically controlled on here. But of course Worcester Bosch started its business with boilers, and it hasn't neglected those by any means. They're still, for most people, the heart of any heating system. And for anybody looking to save money or to make some contribution to the environment, then changing from a standard efficiency boiler to a high efficiency condensing boiler such as this Green Star from Worcester is the best contribution you can make, because the technology means that for every unit of gas or oil that you put into it, you get more heat into the central heating system and the hot water system. That means you're getting a lot more use out of it, you're saving fuel, and of course that means fewer carbon emissions as well. So you win every way. And another hidden feature of this house that I really like is the rainwater harvesting. Now that's a funny term, but what it basically means is taking the rainwater wherever it's drained from the roofs and maybe even from the ground, and feeding it through into a large tank which can be buried anywhere under the ground. In this case it's under the lawn, and this is the inspection cover here, and then that water is stored there in quite a large quantity and fed back into the house through a pump, through a filter system, and it's used in the house for the washing machine, for flushing the loo, and also for the outside tap. Now not only does that save water in terms of water bills and so on, but it also means that it reduces the impact of flooding. So we're going to see an awful lot more rainwater harvesting in the future. And this is the living room. As you can see, it's nicely decorated. It's all been finished, looks a lot different to when they started. And it's been decorated with environmentally friendly paints. Now all that really means is that there's no solvents, no VOCs in there, so they're not harmful to the environment, they're just water based. And on the floor here, it looks as if this is wooden planks, but it is in fact ceramic tiling. Now, with underfloor heating, you can actually use timber floor, you can even use carpet, but it works best with ceramics. And this ceramic tiling gives the effect of wood, but it actually gives a lovely even heat all over the floor. Now, the lighting in these rooms has been done with low energy light bulbs. Using low energy bulbs is the best investment you can make in terms of pounds laid out for carbon saved. So if you do nothing else, changing over to low energy bulbs is really worthwhile. And there's one other thing I've noticed over here, which is a little simple thing, but somebody's left this on standby, and if you just turn the television off at the plug, it can save an awful lot of money over the course of a year. It's a simple thing, but it saves your fuel bills, and of course it helps the environment. And here in the kitchen, I think this has probably been the most dramatic transformation in the house. It really has turned it into quite a nice room, and it's been done with the minimum impact on the environment. The kitchen units themselves are taken from managed forests. That's FSC forests, which have basically